Check, check. Hey, everybody, it's the 14th of January, 2025. This is Aiken PBL live coding from Gimbalabs and Friends. We get together on Tuesdays at 14:30 UTC to learn Aiken together. There's a course that's currently rolling out on the Andamio platform, and I'll take us over there in just a second. But just to hit the ground running, this is where we left off last week. I have Visual Studio Code open, and I have the Aiken PBL examples repo open right here. And we're working through module 201 right now. Last week, we looked at an example of a validator that introduces one way to use redeemers, but nothing else in a spending validator, right? No datum, no input, no transactions, not yet. We tested those and we tried to break these tests just so we could learn a little bit more about how validators and tests work. And then after we did that, we took a look at a second example that introduces the use of datum. Now, we're going to build on what we did last week, but we might want to come back to these examples later. Today, we're going to go as far as we can through the next 5 examples. Maybe we'll get them all done, but it just depends on how many detours we take along the way. But our goal here is to look at validator parameters, reference inputs, signatures, time, and transaction inputs and outputs. By looking at these one at a time, we're going to build up our understanding of what a validator can do, yes, in Aiken, but also in any other on-chain Cardano language. So a lot of the concepts we're going to be looking at right here are still going to apply to your design of validators that you write in another language like Plutus TX or otherwise. Of course, the syntax will be different. And so if you ever have questions, that's something that we can put in our backlog and get to that as time goes by. But hopefully, what we work through right now is going to help everybody get a pretty solid foundation for what are the key building blocks for designing validators that can actually do things. So before we go any further, I'm going to just share screen on the course outline for just a moment. And I'm going to go back to the home page. A lot of you have already accessed the course in Andamio. And now if you go to andamio.io, there's an app button to look for in the top right corner. Once you click the app button, you'll be able to browse courses. And this is where you can find Aiken project-based learning. So ultimately, the URL is a little bit different than it was in previous weeks. It's at app.andamio.io/course and then Aiken PBL 2024. And this link can be shared freely. It's open access. So I'll drop this in the chat one more time just in case anybody needs it. And then I'll navigate to the lesson that we're working on today. It's in module 201. Like I just showed you in the code, last week we went through modules 201.1 and 201.2. Today we're going to work on lesson 201.3 and keep going as far as we can. So let's jump in. This lesson is about writing a parameterized validator. We have the code example. We're going to go back there in just a minute. And what we want to do is start to recognize that in our first few examples, we've written validator signatures that look like this. The name of a validator, the keyword validator, and then some name for that validator. And this is common practice. And we even saw this in the 2 examples we looked at last week. But it's possible to write a validator signature that has a little bit more information than that. Here's an example that takes what we call a parameter. This validator still uses the keyword. It still gives the validator a name. And then we have these optional parentheses. And inside of those, you can define parameters that you want to pass to the validator. This is really convenient for writing reusable code. In this example, this is a minting validator that allows you to mint some unique token with its own unique policy ID. To ensure that uniqueness, we have a parameter because what we're actually going to do when we use this validator out in the wild is we're going to recompile this validator every time we use it. And that's going to allow us to create unique versions of the validator that result in unique policy IDs. And if you can ensure that you have a unique policy ID, well, that sounds like an NFT, doesn't it? So this is a common pattern you'll see in Cardano development for creating an NFT that is truly unique in terms of the policy ID itself. So that's just one use for parameters, uniqueness of a minting policy. But more generally, and we're going to look at examples of this as we go along, anytime you have any set of parameters right here, you can write the internal logic once. Look at lines 14 through 19. This part only has to be written one time, and the logic can be reused, with any UTXO to create a unique instance of this validator. That's really exciting. And this is one thing that allows app developers to build scalable applications, right? Imagine a case where you had to rewrite the validator for every transaction that might pass through your application. Or imagine if you had an application where you had to rewrite the validator every time you wanted to use it with a different like what's the word I'm looking for? Fungible asset, like tradable token, right? If you were building a DEX or something. So really convenient pattern here. And in just a minute, we're going to go into the code and play with it a little bit to understand better how it works. But I just gave kind of a fast-paced journey from what we did last week into the course and now into this lesson. Let me just pause right here. How do you feel about this idea of parameterized validators so far? And do you have any questions at this stage? Yeah, Prince Platypus, it absolutely is the case for Plutus TX. So obviously the syntax is a little bit different, but anytime you're writing a scalable application, you want to really be sure that you write reusable code. So you write your Plutus code in a Haskell file, and then you're able to add parameters there as well. And there's actually an example of this. This might be worth looking at very quickly. If I jump over to Course Studio and Plutus PBL, we're working on updating this course for 2025 right now. But let me just see if we gave you, this is the faucet validator. I think this example, this is the examples. Um, I think this one has, yeah, okay, here it is. Here's an example of a validator that's written in Haskell. And just like in Aiken, let me go back a few pages now to what we were just looking at. Just like in Aiken, any spending validator has datum and redeemer. We see those two things right here. This validator has, let me zoom in a tiny bit. This validator has a datum and a redeemer. It also has script context, which basically encapsulates these two things, output reference and transaction. I'm oversimplifying a little bit right there, but in Aiken, where you see input and transaction, in Plutus, that's all inside of the script context. But then before these, right, these are also parameters to just a Haskell function. So I'm using that word in two different ways. Think of these as the inputs to the Haskell function. Preceding these, we have some params. And so these params right here serve the same purpose as params in Aiken that are expressed like this inside of these parentheses. Does that raise any new questions or ahas for anybody to see like the different syntax for the same idea? Right. So let's go to the code. Let's look at the example. Let's test this thing. And as always, let's play around to see if we can break it. As always, you can use the chat below or ask questions on Discord anytime, especially if you're watching this video later. Let's jump back over to the code example. And I'm going to open up the example that we were just looking at. Right? So here's our, instead of a spending validator like we were looking at last week, this is a minting validator because inside of the validator, we define the minting endpoint, but not the other ones. This validator takes redeemer, but we don't care what it is, underscore, a policy ID. Again, we're ignoring that with the underscore. But this time, we're going to pay attention to the transaction. Let's compare this to the datum example that we looked at last week. I'm going to open these up side by side for just a minute and maybe move this one. All right, so last week on the left, this week on the right. Last week, we built a spending validator. This week, a minting validator. Don't worry so much that these props are on separate lines and these are all inline. What matters is the opening and closing parentheses right here, right? And then inside of those parentheses, we define a couple of things. In a spending validator, you'll notice there's datum and redeemer. In a minting validator, this also is true in any language, Plutus TX as well. A minting validator is not concerned with datum, no datum, just redeemer. Because a spending validator, right? The purpose of a spending validator is to help you unlock UTXOs. Those UTXOs can be stored on chain. And when they are, they can have arbitrary datum in them. But minting, it doesn't make sense to talk about datum because we're only trying to mint a token that doesn't exist anywhere yet. So there's nowhere that the datum for that would be locked. Now, let's bend our brains a little bit to think through the design of something. What if I want a minting policy that does rely on datum from some other UTXO? Is it possible to build that? What tools do I have for pulling, say, the datum from some spending validator, some UTXO that's locked on chain, and pulling that into a minting validator that says, hey, you can only mint this token if this other datum is present? Hopefully that question makes some sense to you. Yeah, well, and that would be a great example of it, Scott, right? Like this would be a way to think about designing a fractionalized NFT. Ooh, I need to make sure that that original NFT is locked in some UTXO somewhere. And if it is, we're going to allow these fractional tokens to be minted. That's a perfect example. Well, there's a few ways to do it, but one of the best ways to get started would be to pass as parameters to a minting validator some datum. And if you can imagine this, right? Last week we saw how to define custom datum. I could use this custom datum type as a type in my validator. I'll leave it to you to keep thinking about that. The only thing I'm trying to demonstrate right now is making these connections between different, between like a spending validator and a minting validator, different purposes. This is what you'll do as you start designing apps that deliver new utility, new value, right? So for now, let's keep looking at this example because there's a few other things that are different. Spending validator, like I just pointed out, has datum. Minting doesn't. But minting validator has a policy ID and spending doesn't. So it's possible to build a validator where we expect a certain policy ID as the input. That's helpful, but we're not talking about it yet. Just want you to have that on your radar. You see the underscore right here. In this example, to get started, we're just using a transaction. And previously, we didn't care about transactions. Look, here's the underscore in front of the TX from last week's example. But the type is the same, transaction. And this time, we're going to use it. So now I'm going to get the datum example out of the way now that we've compared these side by side a little bit, because I want to zoom in and focus on how are we using TX in this example. Just checking the chat. Can the node validate the datum I input comes from a specific UTXO? Okay, that's a really good question. So yes, and it has to. Okay, so when you build a spending validator, it's going to set the rules for the kind of datum that must be in the UTXO that's going to be unlocked in the first place. So actually, by definition, the node is going to accept a transaction. It's going to accept a valid transaction based on the datum in the UTXO that you're unlocking, meeting the requirements of the validator code that you already wrote. So yes, 100% yes. And that's actually a key design of how all of this works. So what I want to look at for this example is just this transaction, right? We're taking some parameter from the validator, a UTXO. Oh, and by the way, that output reference, right? That's the other thing I meant to point out. That output reference has the type of input right here, right? So it's not an input to the minting endpoint directly, but we can pass it to our validator. And what's happening here? Okay, so now we have a keyword when. We might want to talk about that a little bit more. And we have list. Is list being imported from somewhere? Yeah, it is on line 1. So we might want to check the docs about Aiken collection list. And we're running list.find, and it appears that this takes 1, 2 inputs. Okay. So when list.find, we're going to pass it the inputs from the transaction itself. And then we're going to run a function mapping over those inputs, looking for an input such that its output reference matches UTXO, which was the parameter in the first place. Then we have another keyword is, which comes as a pair with when. So like we're basically saying, hey, when you can find, when you find some, return true. And when you don't find some, when you don't find anything in this search, return false. If you find some, return true. Find what? Well, anything. Any successful result right here means we were successful. The underscore means we don't actually care what the matching results are. But as long as there are results, we say, yeah, there's a match. And in any other case, we return false. All right. Wow. Got to pause for just a second here. Maybe you're starting to put these pieces together. There's a few concepts that we already looked at last week, but we're going to want to break this down. So chat for just a second. Does is require when? Okay, that's a perfect question to take us into the docs. We're going to go into the docs and see if we can find a good answer to that. And then datum can't be referenced as input. Okay, also a great question. So, quick history lesson in Plutus V1, the answer to that question was yes. But in Plutus V2, what we gained was the ability to look at on chain datum without spending the UTXO. So moving forward, the answer is absolutely yes. We have the concept of reference inputs in a transaction. Okay. So the way reference inputs work is it just looks for it, right? But without taking it as input and needing to put that datum back on chain, it makes for much more efficient transactions. So here's what I think we should do. I'd like to go into the documentation and find when and is keywords so we can learn a little bit more about those. And then maybe while we're over there in the docs, look up list. Those are my next two action items. But what else? As you take your first look at this parameterized minting validator, is there any other syntax that you want to better understand here that we should focus on in the next few minutes? All right. Well, we'll start here and let me know if there's other things we should look up. I'm going to go over to the Aiken documentation. There it is. All right. We should have the Aiken docs up now. Well, the first thing I'll do is just search when. Mm, that's kind of a common word. All right, so that's not the easiest way to find it. So let's go into the docs itself. Let's look at control flow. Piping, if else, failing to do. Let's see. When. Maybe I'll search this page for when. When. Here we go. Giving a reason. All right, so this is not the direct documentation, but here's another example. And here you see this idea of option. Remember this one from last week, right? We had optional datum. And we talked about, well, when some type is option datum, you're either going to have some datum or none. And so here's the general example, right? Suppose we want to expect some arbitrary value of any type A. We could say, all right, when the opt has some A, return A, and otherwise return none. This is like a commented version of the option, what we're already doing with option frequently in our code. Okay. That might be a helpful example, but it's not a definition. Let's see. When x, let x equal sum 42. Okay, so now it's giving us this concept of non-exhaustive pattern matching. Seems helpful. This example doesn't feel too surprising. It also doesn't feel too realistic right now. If I know that x is 42, why would I want to say it's sum 42? But at least this is accurate syntax. And this is showing us that often we don't need to use when. Why? Oh, because we have this expect keyword. Okay, so when is actually gives us a way to more exhaustive, right? So this heading says non-exhaustive. This is the non-exhaustive case right here, right? We just run through, we say, okay, expect this part. this way to be true? And if it is, keep going. And if not, just stop because there's no reason to keep going with the program. And this is the way to write that by hand. So that's kind of nice. What else? No, those don't really help. Oh, just use when is. Okay. Note that the use of if is discouraged in situations where no type. This seems like a pretty important line right here, just buried at the bottom. Okay. Here's a bunch of examples using if is. The use of if is discouraged in situations where no typecasting is necessary. Just use when is. So even if I don't know what typecasting is, I'm reading that it's encouraging me to use when is. Okay, that's nice. And typecasting is just when we assert what the type is going to be. All right. Often you want to do that anyway. It's best practice. Um, but this gives us a really nice shortcut. So maybe is there something earlier in the docs? Yeah, you see, I'm going back to custom types. The when is block forces us to exhaustively handle. That's what I was looking for. This is really helpful. Okay, in any case, what I'm trying to do right now is just demonstrate like thinking out loud about how to approach docs, right? And so always, always, always look for those opportunities in the code to see a new pattern, and then find it, right? I'm not doing anything special right here. I opened up the Aiken documentation. I guessed that what we were looking for was on control flow. I searched for the word when. I was sort of satisfied with what I found, so I backtracked in the docs a little bit. I hope that this is just helping you feel really confident to go through the docs as well. Um, because yeah, this is a good skill to have. So back to the original question. Does anybody still have questions about this idea? It says it forces us to exhaustively handle every constructor in the type. Anybody want to try to interpret that for us? At the end of the day, this is the reason why we have to use the wild card right here. It says we need to think about every case, right? So we have to know all the things that user might be in this example, or in our other example, what the results of list.find will be. Oh, that sounds interesting. That's the output of some function. This is why we might want to go look at Aiken collection list in just a second, right? But before we do, before we look at what list.find is going to give us, just look at this example right here. When user is, oh, logged in, I see that would be a state for a user to have, fine. And for any other case, right, I don't need to know all of the possible values of user because I have this underscore. And so even though that sounds intimidating that we have to handle exhaustively every constructor in a type definition, the wildcard makes it easier for us to handle that, right? Because yes, of course, if I know there are 5 states a user can have, right, whatever they are, logged in, logged out, canceled, subscribed, whatever. If I know all those states, of course, I can add lines below this one. But in any case where it's impractical to cover all cases, that's another use of this underscore. So you're starting to see the underscore is used for all sorts of different things. Ignoring a variable if you tack it onto the front of the name, or capturing all wildcard, right? Any case of some value that we may or may not know. And now to the case of not knowing, right? We have this function, Aiken collection list dot find in our code. And what I want to do is go find the documentation for Aiken collection. Now, what did I just click? At the top of the page, I clicked on the standard library. And we talked about this last week. Some functions, you'll find them in the standard library. And as you practice, you'll get exposure to which ones to expect here. And over in the prelude, we have some other types and functions defined. And same thing with built-ins, all sorts of built-in functions that Aiken gives us under the hood. All right. But as it turns out, the thing we need is in the standard library. That's what I'm looking for. And one thing to start to generalize, right? We asked this question last week. How do you know what's in standard library and what's not? Well, anytime you see an import from Aiken, that's going to be in the standard library, right? We imported Aiken slash collection slash list at the top of example number 3. And sure enough, here's Aiken slash collection slash list right here. Okay. Let's jump into list, and here we will see the functions, in particular, the one that we were using in our code, find. Where is it? Well, I can navigate on the side menu here, or I can just scroll down the page. And it's easy to share a link to any of these, because I don't know if you could see this up in my navigation bar, but there's a hashtag find at the end of this URL that takes us to right here. So that's the link I'll drop into the chat just so you have it. And yeah, Prince, we'll get back to that in just a second. So let's take a look at this find function. First of all, I hope you're not surprised at this point to see that find returns an option of some arbitrary type A. This is the type of whatever is in the list that we're iterating over, right? So in our example, we were using inputs, and we're going to want to look at that again in just a second when we go back to the code. But look, find, it takes some list to map over and some function, okay? Some function that we're applying to the list to say, hey, tell me what foods you have and return just the fruits, for example. Is fruit or is not fruit? Return the ones that are true, right? Some list of any type, create a rule for filtering them, and find if there's any, right? Now, we're using this as just kind of more of a Boolean thing, because look what find returns. It's actually not a filtered list. It's just the first element satisfying this rule. There's other functions that I can use to complete other operations on this list. And for example, filtering is here under extracting, right? So when we say find, we're just taking a look. We're not building a new list. But often extracting functions are those that take a subset of a list or otherwise manipulate it. And so filter is the one that would actually return a new list filtered this way. So find, yeah, is there anything in this list that satisfies this condition? If so, give me the first one. If not, return none. And that's exactly what's happening over in our example, right? Let's go back to that example for just a minute to look at this syntax. Right? So we say right here, list.find. Now, this doesn't say list, does it? But if we just think semantically for a minute, anytime you give me a plural, I'm going to assume it's a list. A list of what? Oh, of inputs. Okay. And an input has many things, including an output reference. And I'll show you where to find that in just a second, right? And we're taking a transaction. Every transaction, if you understand the UTXO model, you understand that every transaction has one or more inputs. So it makes sense to assume that every transaction has a list of inputs. It wouldn't be a transaction without any, okay? And then we can use list.find to iterate over that list of inputs and run this function. Now, just to be a little clearer about this, let's review transaction. We looked at this in an earlier lesson, but while we're in the documentation, let's review it again. It's impossible to look at the transaction docs too many times. This is something that you really want to be confident about. So Cardano, transaction this time. I'm going to scroll down to where I see the whole thing. This is a good spot to bookmark. Okay. And what does transaction have? Of course, it has inputs. We're using them. And what is inputs? Ah, it's a list. A list of what? Here's the type, right? So remember just a minute ago, we were looking at option and brackets and then a lowercase a. That a just stands for any type. Here we're saying it's a list of a specific type. Of what type? Ah, inputs. What are inputs, by the way? Oh, here they are. What do inputs have? Inputs have an output reference and an output. You saw this for the first time a couple weeks ago at an earlier lecture. Maybe you're seeing this for the second time and it's making a little bit more sense. Okay. And we're going to keep looking at this in different contexts, but hopefully this exploration is helping you build a model for how all of this works. An input has an output reference and an output. Wait a minute. Wait a minute. Going back over here, this input, this input. Okay, so we go over the list of inputs, and for each one, what are we looking at? Ah, of course, dot output reference. Why are we able to look at that? Well, it says in the documentation, the type of input is defined this way. An input has an output reference and an output. And you can keep going in the docs on your own to review the type of output. What's important to us is that there's this output reference that has the type, finally coming full circle. It has the type output reference. And that finally, that's exactly the type of the param we were passing right here. Now, you can use any types as long as they're defined and as long as they match, right? So this is an example using all built-in stuff, right? Types that are defined in the Aiken standard library. This is great, but there's no limit to how you can define your own types. Pass them as parameters, use them as redeemer, for example, and then write logic that compares your redeemer to some params that you pass right here. I leave that as an exercise for you, of course, but we're going to start digging into that concept by looking at, building real logic over the next few weeks. So let me pause right there. That was a tour. I know we were kind of going back and forth between the example code and the documentation. But again, same question as earlier. Does anybody have any new questions after you saw that? Or are there any aha moments and different ways that you might try to say things? I'll go to the chat for now. I hope this is helpful. I wish I could see everybody. But yeah, I hope you're having a good time. Okay, so I'm going to Prince's question. When you finish explaining when is and underscore, coming back to the inputs, might sound counterintuitive. Can I print datum on a UTXO for the output of the transaction that created it? So yeah, datum is added to the blockchain as the output to some transaction, full stop. But you can't use an output created by a transaction as an input to the same transaction. That's not possible. It is possible to build server-side infrastructure, for example, where one transaction must be successful before you initialize the next one, right? So I can say, look, transaction A is going to have this output. As soon as it succeeds, transaction B is going to use that output as an input to the next transaction. And in fact, you can even do that before putting anything on chain because transaction hashes are deterministic, right? even before I put a transaction on chain, I know what its transaction hash is. And that's what allows me to build sets of transactions before even trying to place them on the wire. So yeah, lots to play with there. Really interesting advanced topics to go into. But yeah, hopefully that helps in terms of the big picture. Well, so finally, let's test this thing and be sure to chime in if you got questions. This is a little bit more complicated than examples we've looked at before, because in this case, we have to build a mock transaction. Now, I'm not going to review this all from scratch. There's a reason we started with this at the beginning of the course. And if you want to review this, go back to those earlier lessons, right? And take a look at how different ways of building a mock transaction are equivalent. You can find all of it here in Module 103. All right. For now, we're going to assume that we've got this stuff down. And look what we're using. We're saying use mocktail TX, and we're gonna apply, okay, this is a pipe and a little arrow. We're gonna apply this TX in to it, and then we're gonna complete it. And what is that gonna give us? It's gonna give us a valid mock transaction. If you're not too confident with this application syntax right here, don't worry about it too much. Just assume that this is all boilerplate. And the part that really matters to you is right here for now. What do we need to have in this transaction in order to make it a useful test? Well, this is unlabeled. True mock TX hash 0 from Lovelace. This is where I really want to look closely at this documentation to understand what each of these parameters are right here. So let's see if we can find that. I'm going to go back to mock. Let's see if we had anything in our unlocking TX. And I'm looking for an input. This says an input. I don't know about that because it's not a mock transaction of the mocktail variety. Let's see. Oh, that looks more familiar. Oh, okay. Wait a minute. Wait a minute. This is once again true. Where are these coming from? Okay. Now I got to remind myself I'm in a test right here, or I'm preparing for a test. Right here, I'm just already directly in the test and defining this thing in line. And
What exactly you're looking for?
I'm looking for what are the definitions of these five props right here.
Uh, I see. There's a online documentations that got everything. So get into the web post. Let me send the link in the chat.
Just in time. How long you been here? I didn't even know you were here.
Yeah, I've been here all the way.
Hey, what's up? All right,
Yep.
let's open up
It's
the vodka documentation and find this. So I'm looking for Mocktail TX.
yep,
Mocktail.
just mocktail and you
Start at
found
the
it.
top. Oh, here it is. Transaction. And here's Mocktail TX.
Yes, and right
And I want the
on
in.
the left hand side.
Yeah.
Yeah.
TX in. Here it is. Okay. So we need the condition, the TX hash, the index, the amount, and the address. All right, I'm going to keep this open and go back to the example. Just comment this up. So this is condition. This is TX hash, which makes sense because it says mock TX hash. Very nice.
Or is it just me cannot see the screen?
Oh, I didn't. I got almost there and didn't press the blue button. Sorry about that.
I see, I see.
This is our TX index. Then we've got an amount that makes sense, amount of Lovelace, and a mock address. Perfect. All right. Probably could have inferred some of those things, but tell us about this condition right here. It's just defaulting to true, I guess. But what did you have in mind when you added condition to TXN?
Yep. It's actually a convenient design for multiple case testing. For example, here we could define a variable called is the input included. Then we could just dynamically pass in true or false for different test cases just to yeah build different transactions easily. There are some working example in the mesh repo. I could also send it out for reference.
So earlier I mentioned that kind of just thought experiment of trying to build a spending validator and a minting validator that somehow interact with each other. This condition gives you a way to build those interactions into your tests. You could essentially say, okay, well, if some previous condition is true from some earlier dependency, then you can mark that here. Otherwise, you can stop the test before you continue. Am I saying that right?
Yep. Just if the first condition is marked as false, you just think about the whole TSN will be ignored.
Right,
Just didn't run the whole thing. Yeah.
right. Yeah. And that's actually a nice parallel to what Prince is talking about in the chat, right? Like we have the ability to say, okay, this second transaction is only going to matter to us if the first one was successful, right? This test right here, this mocktail transaction is only going to have inputs if some previous thing was successful. And otherwise, ignore it, break. Yeah.
Yep. Or sometimes we could use it on the other ways around. Like for example, testing some case like double satisfaction. Like we want to intentionally include double inputs. So we just duplicate these lines and yeah, for the second duplication, we could pass in a the dynamic Boolean like is there double unlocking attempted, something like that, just to mock different scenarios.
Right.
Yeah, I've just sent out a link in the chat, which is in the mesh repo in other contrast. I got some example about how to best use this pattern, in my opinion. Yep. Like this cancel test case, I could define different scenario
Hmm.
and then just dynamically pass into different places to build the transaction
Yeah. Yeah. Yeah.
so that
Is at initiation is one case. So if we have that,
then we run that.
yeah. Cool.
Yep. And
Yeah,
then
yeah, yeah, yeah. Cool. Okay.
yep. And then we could just run different test case very neatly, just like 99 and below. We test different complex scenario according to the combination of different true or false.
And
And we could expect it pass or not passing.
this is beautiful because once you've put this work in, you're halfway to writing like the front end logic or whatever,
Yeah,
right? Any
exactly.
transaction library logic. You look at this, you're going to say, well, okay, we're going to need to confirm that is initiator signed and is recipient signed in our app. We're going to have to
Yep.
define, right? This is just a test right now, but you can imagine there's going to be a cancel button somewhere in the app.
Yep. Then for those TS builder function is actually following exactly the same design pattern of mesh case builder. So we could just directly migrate kind of. Although still have to add in some ignore logic like collateral and select UTXO, etc. Yeah.
Yeah. That's really good. That's a really good insight. All right. Well, to to keep it moving a little bit, I know I took a lot of time kind of going through this example, but I hope it's helping us build some momentum here. Oh man, Prince, that's exactly it, right? Yeah, your goal is to have absolute 100% certainty that no one is ever going to be able to build a transaction that you don't want them to build, right? That's non-negotiable, but at the same time, you want to achieve that goal for as little transaction cost as possible. So that's a fun problem, right? How do you build the most efficient validation that will always ensure that the results you intend for are going to be possible? And it's got to be perfect, right? If we're talking about being able to move value the way we are, right? It's some cost is of course warranted, but getting it right is hard. Beautiful. So if we go back to this example now, here it is. Let's do this. I'd like to run. Am I in the right directory? Yep. There's my Aiken TOML file, right? That we're going to rely on in order to be able to run any tests and not npm. Aiken, check M. And let's copy this whole string right here. So we only get this test. Yeah. Looks good. Aiken. Do I need I'm in Z shell. Thought I had it right here. Um, there it is. That's better. Okay. We have missing. Oh, that's in data. No, that's because I was messing with that. I don't. Oh, what did I leave something over here? I didn't mean to. Line 39. Oh, I was playing around with all this other stuff last week and left it there. Let's give me 1 second to fix that. There we go. Good. That's what we're looking for. I had an error in the code from last week just because I left some half-done stuff at the end of our lecture. That's why we had that error. Now we have what we want. Let's clean that up just a little bit and look at it. All right. So as we would hope to see, this is a passing test. Sure. My question for everybody is, can you suggest one thing to change in this test that'll make it a failing test instead? What can I change? Just one thing that'll give us a fail right here. All right, I mean, I'll start. I just heard Hinson tell us about this condition line right here. What if that was false? Would that be one way to get a failing test? Let's see. Yeah, that's one way. Okay. right? So if this transaction is marked with a false condition, we're not going to be able to use it. We're not going to have the transaction we expect, and we're not going to be able to run this test. Can you imagine any other ways to make this test fail? Let's see. This minting policy, mint, it has four parameters right here, four of them. Minting by default has three. It has redeemer, policy ID, and transaction. The reason this test has four is because the first one is our parameters. Okay. Yeah, exactly. Right. So this parameter right here has a hash and an index. This is like a hash index and an index um, to get the right mock UTXO ref. Just under the hood, Mocktail is providing us just lists. But yeah, let's change the mock TX hash index. I could change it right here or right here. What if I make this a one? Then I would expect, yeah, a failing test. Now, if I change it in both places, is there a chance it'll come full circle and be a passing test again? Sure enough, good, right? So remember how mock UTXO ref works. It's going to take the hash at just some arbitrary index and then some integer index. And this same thing here. I could turn this into a one, this into a one. Let's make both of these fours. That should be a passing test as well. Sure enough, right? If I go too high, how many mock transactions does Mocktail actually provide? Does it have six? Yeah, it does. Does it have 26? Still. How high do these indexes go? Anyway, that's pretty nice. Cool. I could also play around with the policy ID. Could I? Mock policy ID 0. No, that's not implemented here, so that shouldn't matter. And it doesn't matter in the validator anyway. Here's our datum. I'm just passing nothing, the void to it. And then our transaction, of course, is the one that's taking these values. Cool. So I'm going to leave this right here for now. And let's jump to the next example, reference inputs. And this is going to get at Prince's question from earlier, right? In this case, I want to be able to take a look at an input without spending it in the transaction. What we're going to do is write a spending validator. We're no longer going to have a parameterized validator, but of course we could, right? You can take any of these examples and try to parameterize them by adding your own and placing them in the logic. But for now, this is just an unparameterized spending validator where we only care about the transaction. And actually, there's only one thing we care about in this transaction. It's whether the transaction has reference inputs. Look, hopefully, because we spent a long time in the docs a few minutes ago, hopefully some of this syntax is starting to look friendlier. When TX, what's TX? It's a transaction. You know where to find the docs for that. And you can confirm for yourself that a transaction has a reference input field. And because it's a plural, we can kind of expect, okay, that's probably a list. You can confirm that in the documentation as well. And you can find the type, what kind of list. But all we're looking at right here is if there's anything in that list, validate. And if that list is empty, right, any other case, don't validate. And that's all there is to it. Of course, it gets a lot more interesting when you care about what those reference inputs are and you validate against, say, the datum in them. That gets really interesting. That's where you start to build one validator that might talk to a UTXO somewhere else, stored by another validator. right? So really quickly, we can jump straight from here. Simple logic. Does it have reference inputs or not? Hopefully, this feels approachable to you because you know where to go to look at the docs. You know how to learn more about reference inputs, and you can start to imagine writing custom logic based on the actual contents of this list. Let's look at the test. Here, we build a mocktail TX, and what do? We actually add one, two, three reference TX ins to it. And we see this test field that Hinson described a few minutes ago. Here's test cases. Each of these is going to be a Boolean. So is ref input present? This can be true or false, just like in the examples we saw before. Same thing here and here, but with the other property, right, on test case, also a Boolean. For each of these reference TXNs, we define a mock TX hash, the index, the Lovelace, and some address just like before. And now we can use this mocktail TX in our tests down here. Let's run these and then take a look at what each of them is doing. So this time I'll say just L4, and that prefix should get me all, how many tests? One, two, three tests. Let's see. Yeah, there they are. Okay, they're all passing, fine. But now we want to kind of understand what were we testing for. In the first one, we actually finally define the TX as a mock TX, right? From right here. Okay, so we're passing the test case in. What cases do we want? We want the case where input present is true and multiple ref inputs is false. If we pass this in right here, check reference inputs. Oh, this is checking to see that we can have a UTXO ref at 0, 0. This says 0, 1. Why 0, 0? Hmm. I would have expected this 0 and 1 to have to match this as a 0 and 1. Because this is the one where input is present. Oh, this is just any. Oh, right. But this is just saying, is there any at all? Right? It doesn't matter what it is. Okay. So the reason we don't care which actual ref UTXO it is. We just want there to be a non-empty list. Okay. So actually, if I marked this one false as well, then it would match this case down here where we expect it to not validate. This says won't validate. All right, so if we set both of these to false, then this one's false, this one's false, and this one's false. There will be no reference TX ins, and this will return false. Let's confirm. Sure enough. Okay. So I'm trying to just think through how do I take these examples based on what I understand so far, change them a little bit so that they fail, and ideally be able to describe why. Now, if the other one was true, then we would have the third example. Yeah, that's fine. And by the way, just for fun, just to really get around, how these patterns match, what if what if the how do I say an empty list? I would love to just reverse this logic right here. When TX reference inputs is, does that work? I actually don't know if that works. Let's see. Oh yeah, that works. Okay. Okay, so when the list is just an empty list, return true. Otherwise, if there are items in the list, return false, right? So now we've negated this, and the ones that are passing are the ones that well, this one should pass. False, false. Oh, this one. No, maybe not. I said false, false. I would expect. What am I missing? False, false should pass every other case. I got to review my syntax. I'm not sure exactly what pattern this is matching if I just do empty brackets. Oh, because this said not. Wait a minute, wait a minute. That's why. It's the not here that's killing me. Okay. I want, if I say false, false, then there will be no reference inputs, and this should return true. If I say this is the same, if I say true, false, or true, true, if there's any reference inputs in any way at all, then this thing should fail like this. Okay, I would expect all three of these tests to pass. Yeah, that's good. You see why that's working? And I was confused because I didn't notice there was an exclamation point down here. But you see how now we changed the logic. This is a validator that will only work when there are not any reference inputs, and then it'll fail in any other case. And then if I put the underscore here, this is the one where there are any reference inputs. And if I change that, now all three of these tests should fail. Now the third one still passes because oh, right, because it's expecting not to be true. There. So in any case, playing around, I actually was genuinely confused there for a second. So that was fun. And hopefully, again, just trying to model for you ways to talk through the code as you start to understand it. Play with the test cases. Assume that there's a reason for everything, right? So like I was confused about why I was getting a result right here I didn't expect, and then just had to look. Oh, the bug was there was an exclamation point. Cool. I think we have time because we can start moving faster now. Now that we have some patterns for thinking through these things, let's see if we can move pretty quickly through signatures. So, a couple patterns to apply when we open up a new example. This one, it's a validator. What kind? Spending. Does it have parameters? No. What are we accounting for in the validator logic? Okay, the datum and the transaction, but not the redeemer and the input. Good. So in just a few moments, I can have a bit of a picture of how this validator compares to the other ones I've seen in the past, right? No parameters, spending validator, datum, and transaction are what matter. Cool. What's the type of the datum? That's defined up here. It has a single field called owner, which is a byte array. Okay, keep that in mind. When we come to the logic itself, we're only going to validate if there is some datum, right? Remember, that's what expect is. It's a shortcut for covering only the success cases. If there's no datum, this validator fails right here. It doesn't even keep going and it returns false. Okay. If there is some datum, we continue and we call that datum. You see, expect datum up, right? Expect some datum in datum opt. And this is the pattern we apply. If there is some datum, call it datum so that we can access it right here. And what are we doing? We're calling a new function that maybe we haven't seen before called key signed. It takes tx.extra signatories and datum.owner. Well, datum.owner is a byte array, so I would expect tx.extra signatories to also be a byte array. And to check my understanding, I'm going to navigate back to the Aiken documentation, find key signed. It looks like it's in cocktail. Okay. I'm going to find that function and I'm going to understand what's happening right here. Now, cocktail is still in the vodka library. Hinson already shared some links to that with us. Um, but notice right here, it's actually in cocktail. What does that mean? It's spicy. It's actually on chain,
Yep.
usable anywhere.
Non-spicy for a test case.
Okay, we have a real ABV in this cocktail right here. None of that in the mocktail. Let's go figure this out. I'm gonna jump over to my browser again, and I'm looking for the vodka documentation. Cocktail, where's that gonna be? Extra signatories?
Actually, could just click cocktail. Yeah, extra
Oh, right. I
signatory
forgot to do that. Yeah,
is
yeah.
a
I've done that twice. All right. So now I can find key signed. Here it is. Nice. And so the vodka docs are formatted like the Aiken docs. That's beautiful. Makes me feel a little more comfortable. Thanks, Scott. Yes, that's it. And so what do we have here? Key signed is a function that takes a list of byte arrays and a byte array and returns true or false. Wow, this actually looks very similar to this output scan with the list we were scanning a few minutes ago. Where was that list? Aiken collection list, right? So we looked at find, which took a list and some function and returned us the first one, if any. And we were kind of able to use this as a Boolean because of the way we wrote our validator, right? If there's anything, return true. So there's a similar pattern going on right here. Key signed, look at a list, and instead of running some predicate function, just pass a byte array. But also keep in mind, this could be used as a predicate function in some other function. But for now, it's good enough to say, look, we've got a list of signatures. Look for one of them. And if you find it in that list, return true. Why does a transaction have a list of signatures? Because multi-sig is possible, right? It's possible to have many parties sign a transaction. Often, for simple transactions, you'll be the only signer of a transaction from your wallet. But even when that's the case, there's still a list. It's just a list of length one, your signature, right? And then any other transaction, there can be many. And this is going to be very common when you build systems on top of Cardano, is that you might have a contract that does expect multiple signatures. And we can check for those. Okay. And you'll find that up and down from right here in the validator view of looking at extra signatures and then somehow using them. In this case, all we're doing is checking that the transaction is signed by whoever is specified in the datum. And this is the first example I think this is the first example we've looked at that I think would actually be safe to use on chain, right? Because you can publicly say in a UTXO, hey, I'm putting a UTXO up there, but it can only be claimed if the transaction is signed by the owner specified in the datum. That's a pretty simple pattern. It's common enough, and you're going to see it piece by piece. So definitely realistic enough. Nothing special here, but a basic escrow. That's pretty cool. So now we look down here at the tests. Hinson, what were you going to say?
Yeah, there is actually a more detailed documentation. There's a hyperlink, the place that you
Oh,
just
nice.
visit.
Oh, yeah, right down below. Thank you. Let's go
Yep.
there.
Just Cocktail is a place that I we export everything. But for the detailed documentation, there, yeah, in the subfolders, everything's.
Got it. Yeah, and it's in extra signatories. That makes sense. And so here we have a Boolean test. Here's an example of a list, and we just compare. And these don't have to look like real keys because it's just a byte array. So this code would work.
Yep, just a demonstration about the logic. This
Yeah,
is easier to understand.
very nice. So to wrap up, a quick look at those tests over there. It's really hard for me to know if we're going like too fast or too slow. Um, so be sure like to drop a line like Discord later if there's questions that come up, and if anybody wants like a faster paced session or anything, we can adapt to what people are feeling. But for now, let's take a quick look at these tests. How many are there? One, two, three. Here's our mock transaction. This pattern is starting to look pretty familiar right now. We're implementing a mocktail TX, but really the only thing we care to specify in it is the required signer hash. Here it is. We have a condition right here, which is defined here. So that pattern is starting to feel familiar. And we pass along a mock pub key hash, which is provided by Mocktail, just like it provides some, mock UTXOs, so we don't have to write them over and over again. Same thing with pub key hashes, for example. So we can pull that in. So what do we say? We say that we're going to build a mocktail TX with pub key hash 0. And then we're going to expect if the owner is 0 in the datum, this one should be successful. But if the owner, oh, this is just is key sign, right? If we don't have the signature, fail, or if the owner is other than the one, if the signer doesn't match the one in the datum, that's going to fail too. So success means they signed and uh, this matches, and it fails if they didn't sign or if there's a mismatch. And that's realistic too. It makes sense to provide is key signed as a condition right here because in our tests we don't know, right? We can't know if somebody's going to try to spend from our validator without signing the transaction until we put it out into the wild and somebody actually tries, right? So this test, we're just saying, okay, well, in the case where somebody doesn't sign, will this validator fail? I hope so. And in the case where somebody signs and there's a match, yes, that's the success case. In the case where there is a signature, but it's the wrong one, of course, we want the validator to fail there too. So let's double check. Let's do L5. We'll see our three passing tests. And just for fun, really quickly, if I change mock pub key hash 0 here to a 2, then I'll get a failing first case. If I change this to a 2, now they will match again, so it'll pass again, right? And if I made this one match where it's not expected to, then that one would be a failing case. And sure enough, that's what we see. So I think that's good for today. It's going to take us 3 weeks to go through these 7 lessons. I think it's worth it. Um, I think it's really worth it to dig into each of these concepts one at a time. And hopefully, if you're following along with all of these lessons, you're starting to feel that it gets easier to look at each example. So maybe next week we could start, but move quickly through time and inputs and outputs by applying the patterns we've already learned here. And then Hinson's going to take us through module 202. Yes, sir.
Yeah, sounds good.
For next steps, that sound okay?
Yep, perfect.
All right. Thanks for attending. If you're catching up with this later, what's up, Hinson, Scott, Newman, everyone? Um, Yeah, I'm excited to keep aligning on if we're moving at the right pace, but really excited also to finish this first wave of lectures. We're going to keep live coding going after delivering the initial lectures. And that's where the agenda turns from first time through everything and into whatever questions people have as they're working through. Hinson has some plans to get us going with that. So after we deliver module 301 a couple weeks from now, Hinson has planned, what are we doing? A crash course in bad contract design?
Yep. Actually, it's both of a example contract design and the bad contract, or cover a little bit of common vulnerability. This is coming from the mesh repository, like the example that I just sent out. And recently just also produced some bad contract example like unbound value, double satisfaction, a couples like 4 to 5. Like just as an example about what we usually want to think about when we decide the contract. So those things is coming from my previous experience interacting with auditors, like really getting the common vulnerability types and try to extract a little bit that a few that I have considered them and put it in the my contract in different places. So it should be fun. And
Yeah.
all the coding pattern, everything is the same, like the way we write on-chain code and also doing unit testing, everything the same. And I use the test case to demonstrate how those vulnerability happens. So yeah, there's a little bit of spoiler, but it should be fun.
I'm pumped about that. And yeah, thanks. That's really exciting. So, firsthand experience with auditors, you've learned what not to do, and we get to go on that journey too. Very, very cool. Yeah, thanks everybody for attending. If you are watching this video later, you can see links to any current Gimbal Labs meetings at gimbalabs.com/calendar. This meeting happens on Tuesdays at 14:30 UTC, and it's going to continue for the near future, at least the next few months. We'll probably go up right up to the summertime, with a few weeks off here and there. I know Builderfest is coming up, so we probably won't do the live session there because hopefully a bunch of us will be together. Um, but yeah, looking forward to that. Really looking forward to the what not to do sessions after we finish the delivery of the next 2 lessons, 202, 300, and 301 to close out the course. And then we're going to keep having open time here to keep going. I know we've got the Asteria crew in the house too. So hopefully there's some really fun Aiken topics to look at there. And yeah, to the question in the chat, there's no playground today. Playground's going to go on a little hiatus. We're figuring out what to do next with it. But that's the general theme of everything at Gimbal Labs. This time of year, we figure out what to do next. We got Harsha and Newman going to pick up the driver mapping workshop on Thursday for any people who want to talk about that question. What are we doing next and why? Thursday's meeting is the place to jump into that. All right, all right. Perfectly on time. Appreciate you all and catch you soon. Take care, everybody.